Calc students, thanks for tuning in to watch the company's revenue problem. We know that you have a choice of watching videos for calculus. Thank you for choosing the company's revenue problem. Here is the story. This is a differential equation application problem, and we know that a company's revenue is earned at a continuous annual rate of 5% of its net worth. At the same time, payroll obligations amount to $200 million a year paid out continuously. Here's how to think about this. Things are happening to this company's net worth. We'll call it is called W. It's got an amount of money there, and because it's invested in things, it comes back to bring 5% of its net worth. So, and I will call that like 5% of W, or 0.05 of W goes back in. So that money is growing. At the same time, or like once a year, it also has to shed out 200 million. So there is a differential going on. There's an amount coming in and there's an amount going out. Part A says, write a differential equation that governs the net worth of the company. So with that picture, we know that the change of the net worth per unit time, or regards to time, is 0.05 W. That's what's coming in, but minus 200 million. And in this case, our dt is time would be in years. That's our differential equation, and that's part A. We solve now for part B, which says solve it with a net worth of W sub $0 million. That's like an initial investment or initial condition. That means W of 0 time is W sub 0. That's the initial value. So this is now we're going to separate this differential equation. Now I'm going to put it in green right now, the way that we'd normally do it if you didn't do any like way forward thinking ahead of time. We would take 1 over 0.05 W minus 200, dW equals dt. We'd integrate on both sides, and you would have to make sure that you adhere to the chain rule for this one. So it's going to be a little bit messy. I would instead encourage you to think about it this way. Let's just play around with that part on the right, and let's factor that number out. So 0.05 is 5 out of 100, so that's 5 100ths. W minus, and then like 2,000 divided by 5 100ths is like multiplying by 20, so that's W minus 4,000. If in doubt, write it out. Double check that if you distribute that's what you get. But I think it's a little bit easier to factor that part out and then do our separation of variables. So we have 1 over W minus 4,000 dW equals, I'm going to make 5 100ths 1 out of 20, yes, 1/20th dt. That's a little bit easier. I don't have to contend with the U substitution there, and I don't have to like mess up with the fractions. So now I'm good to go with integration from both sides. That means natural log of W minus 4,000 equals the antiderivative of 1/20th is just dt, is t over 20 plus c. Now we have done this quite a bit. We want to isolate W, so we need to take the e to the power of both sides, and that means we've liberated W minus 4,000, and we have e to the t over 20th plus c. Now, I'm going to keep putting an equal sign there to make sure that that is e to the t over 20th times e to the c, and know that e to some constant is just going to be a constant for right now, since we're still in general land. So w minus 4,000 equals c e to the t over 20. This is a standard piece that it resolves to when we're dealing with growth or decay. So w equals 4,000 plus c e to the t over 20. That's our general equation. For now. And that is part B, which said to solve the differential equation assuming, a net worth of W sub 0 million dollars. We haven't done that quite yet. We need to now invoke that initial condition. So now use the fact that W sub of 0 equals something called the W sub 0. So that means wherever you see a t, you put in a 0, and the initial condition is W naught. So it looks like this. W starting, W naught, equals 4,000 plus c e to the 0. That means W sub 0 equals 4,000 plus c. C equals W sub 0 minus 4,000. And it feels kind of weird, but that's actually the, let's see, that's, what would I call that? Like the overage, or if you want to make more money, 4,000 is your sweet spot. That is like the equilibrium point. And I'll show you in a minute why when we graph it, it's going to be like that. Let's go back to, so W of t equals 4,000 plus W naught minus 4,000 times e to the t over 20. That is our specific equation. Now, I'll show you let's see, if I can do this on, I graphed these on Desmos, and there's a picture of those graphs. Now the green one is this one where if I start with $4,000, it's like my steady state. That means if I start with, and that 4,000 is not $4,000, I think that's like $4 billion for this company. That means revenue coming in and expenditures coming out stay where they are. However, if you, let's see, this top one here is the blue one down below. It's blinking right now. If you started with $3 billion, you will eventually, after what, 20.8 years, not have any money anymore. You need to start with a little bit more. If you have over $5 billion, I'll make this purple one blink, that means you're starting at, you're above what you need to be in a steady state, and your company will grow over time. That's kind of fun. You can play around with, if you want your company to last so many years, how much do you need to start with in order to, knowing that you're going to be shelling out $200 million and making 5% each year, how much will you need to start with? You can also do this on the graphing calculator. I put one there to find something similar. You'll just have to put in those values, and I don't think there's a way to copy it. However, that's differential equations in a nutshell. Thanks for watching.